Fire is destructive, but the tools we rely on to fight it, water and chemical foams, can inflict just as much damage, completely ruining sensitive electronics, archives, and the structural integrity of a building. In 2008, a fire broke out aboard the USS George Washington. The blaze, combined with the millions of gallons of water pumped in to suppress it, resulted in $70 million in material losses. That specific disaster prompted the Defense Advanced Research Projects Agency, or DARPA, to launch the Instant Fire Suppression Program. They needed a dry, zero-waste alternative to traditional firefighting. To engineer a new solution, we have to look at the mechanics of combustion. A fire relies on a fire tetrahedron, a precise, continuous mixture of heat, fuel, oxygen, and a chemical chain reaction. Standard methods attack this geometry by stripping away heat with water or smothering oxygen with foam. DARPA researchers tested a different approach, shattering that tetrahedron using invisible acoustic pressure waves. Making a small flame flicker near a speaker in a lab is relatively easy. Engineering a device that outputs the precise acoustic energy required to reliably kill a fire is a massive leap. Sound travels as a longitudinal mechanical wave. As it moves through space, it rapidly pushes and pulls the surrounding air molecules. When you direct this wave at a fire, you create a blow-off mechanism. The rapid oscillation aggressively disrupts the flame's boundary layer, physically tearing the fuel vapor away from the oxygen faster than the flame can maintain its chemical reaction. You might assume that blasting a fire with the loudest, highest-pitched sound possible would be the most effective method. It isn't. High-frequency waves vibrate too quickly to physically move a large volume of air. The required energy comes from low-frequency waves, specifically those between 30 and 85 Hz. These lower pitches have much longer wavelengths, which generate the heavy, sweeping, bulk air displacement needed to physically rip the flame apart. This DARPA report data shows the direct relationship between frequency and air movement. Looking at the bottom graph, we see that total air displacement hits an optimal peak right around 60 Hz, reliably causing the flame to extinguish. Identifying that 60 Hz frequency is only the first step. Without a mechanism to capture and direct those specific waves, the acoustic energy scatters harmlessly into the room. The physics of sound presents an obstacle known as the inverse square law. Normally, sound radiates outward from a speaker in a 360-degree sphere. Because it spreads in all directions, its intensity and its ability to displace air dissipates incredibly fast over a short distance. To stop this energy loss, engineers attach specifically shaped physical barriers to the front of the speaker, known as collimators and narrowing waveguides. This technical report illustrates a modular collimator setup. By enclosing the output, the geometry of the tube traps the radiating acoustic energy and forces it forward into a concentrated planar wavefront. This design generates a 6-fold increase in sound pressure at the speaker face, focusing air velocity onto the fire without requiring any additional electrical power from the amplifier. Mastering that exact physical shape transforms an ordinary commercial subwoofer into a precision acoustic cannon. These photographs from a 2023 experimental journal show the device deployed against a liquid fuel fire. The targeted sound waves tear the flames apart and extinguish them in seconds. It is highly effective on both gas and liquid fires. However, the system struggles with solid fuel. When used on burning wood or coal, the intense air pulses can inadvertently scatter embers, increasing the risk of the fire spreading or immediately reigniting. Despite that limitation, the logistical advantages are immense. Acoustic suppression leaves zero residue, requires no chemical refills, and low-frequency sound waves naturally bend around physical obstacles to hit hidden flames. This makes the technology ideal for environments that cannot tolerate moisture. Massive server farms and complex electrical control panels could deploy automated acoustic cannons to isolate and neutralize fires without destroying the surrounding hardware. The highest value application might be off-planet. Aboard orbital platforms and spacecraft, spraying water or chemical foam poses a severe threat to life support systems. A zero-gravity, zero-water acoustic extinguisher solves a massive safety problem for astronauts. By optimizing the hardware geometry and isolating the exact frequency that moves the most air, we can reliably disrupt the chemical chain reaction of a fire using nothing but sound.